a folder full of files, a family tree, and the way your computer stores a maths expression all share one shape. That shape is called a tree. Welcome. In this chapter we learn what a tree is, how to count its parts, and how to walk through it. Let us begin. Hello and welcome. This is chapter 11 and it is about trees. A tree is a special kind of graph. It is connected so you can get from any dot to any other dot. And it has no simple circuit, so no path loops back to where it started. You already know graphs, so trees will feel familiar. We will learn the words, count the parts, walk a tree in 3 orders, and grow a tree inside a bigger graph. This is the plan for the whole chapter, 5 topics in order. First, we introduce trees and the words that come with them. Then we look at where trees are used in the real world. Next comes tree traversal. That means visiting every dot of a tree in a set order. After that, spanning trees. Those are trees hidden inside a bigger graph. And last, minimum spanning trees, which pick the cheapest such tree. In these slides, we cover 3 of the 5: introduction to trees, tree traversal, and spanning trees. Section 11.1. Introduction to trees. We learn what a tree is, how to root one, the words for its parts, and a few counting rules. This is the plan for this section, 4 parts. First, what a tree is. Then rooted trees, where we pick one dot to be the top. Then trees as models, which shows some real uses. And last, properties of trees. Those are counting rules that always hold. Let us look at each one in turn. Let us start with the definition. A tree is a connected, undirected graph with no simple circuits. 2 words carry the whole meaning. The first word is connected. It means you can walk from any dot to any other dot along the edges. Nothing is cut off. The second phrase is no simple circuit. Recall, a simple circuit is a path that starts and ends at the same dot and never repeats an edge. So a tree has no closed loops anywhere. Every test we do comes back to these 2 words. Look at the figure. 4 graphs, 6 dots each, named G1 to G4. We test both words on every one of them. Start with G1. You can reach every dot from every other dot, so it is connected, and no path closes back on itself, so G1 is a tree. Now G2. Again, every dot is reachable, and again there is no loop, so G2 is a tree as well. Now G3. Follow the path E, B, a D, and back to E. That path comes back to its start. It is a simple circuit, so G3 is not a tree. Last, G4. The dot D sits on its own with no edge at all. You cannot reach it, so G4 is not connected and it is not a tree. A related idea has a nice name. A forest is a graph with no simple circuit that is not connected. So a forest has no loops, but it comes in separate pieces. Look back at G4. It has no loops and it is not connected. So G4 is a forest. It breaks into 3 pieces. The first piece is an F, joined by one edge. The second piece is B, C, and E, joined by 2 edges. The third piece is D, all alone. Each piece has no loop and is connected inside itself, so each piece is a tree. A forest really is just a group of trees standing side by side. Now a very useful theorem. A graph is a tree exactly when there is one and only one simple path between every pair of dots. This is an if and only if, so we prove it in 2 directions. Step 1. Start with the forward direction. Let T be a tree and pick 2 different dots, X and Y. Step 2. T is connected, so there is at least one simple path from X to Y. Step 3. Could there be a second path? No. Two different paths between the same pair would join up into a closed loop, and a tree has no loops, so the path is unique. Step 4. Now the other direction. Assume every pair of dots has exactly one simple path. Step 5. A path always exists, so the graph is connected. That is the first word of our definition. Step 6. And a circuit would give us two different paths between some pair. We said there is only one, so there is no circuit. Both words hold, so the graph is a tree. Where do trees show up? Almost everywhere. In computer science, chemistry, geology, botany, and psychology. A bit of history. Arthur Cayley used trees back in 1857. He was counting isomers of hydrocarbons. An isomer is a molecule with the same atoms but arranged in a different shape. That is Cayley in the picture. He lived from 1821 to 1895. Two everyday uses are worth remembering. The first one is a file system. The top folder branches into subfolders, and those hold files. That is a tree. The second one is an organization chart. The president is at the top, and branches lead down to each role. Once you see the tree shape, these all feel like the same idea. Let us see the idea Cayley started from. Draw only the carbon atoms of a molecule and join two atoms when they are bonded. What you get is a tree. The first molecule is butane. Its 4 carbon atoms sit in a straight chain, one after another. The second one is isobutane. It has the same 4 carbon atoms, but one of them sits in the middle and holds the other 3. Both trees have 4 dots and 3 edges. The atoms are identical, only the shape is different. Chemists call 2 molecules like this isomers, and Cayley counted them by counting trees. Now we root a tree. To root a tree, we pick one dot and call it the root. Think of the root as the top of a family tree. Then we point every edge away from the root, going downward. Now the important part. The same unrooted tree can become many different rooted trees. It depends only on which dot you pick as the root. The first picture is a plain, unrooted tree T. In the second one we picked it as the root, and the whole tree hangs down from A. In the third one we pick C instead, and now the tree hangs down from C, same dots, same edges, but a very different shape once we choose the top. Rooted trees borrow their words from family trees and from botany. This table collects them all in one place. The parent of a dot is the one dot just above it, joined by an edge. Every dot has a parent except the root, which has nothing above it. Going the other way, a child is any dot one step below. Siblings are dots that share the same parent, just like brothers and sisters. The ancestors of a dot are all the dots on the path from the root down to it. We do not count the dot itself. The descendants of a dot are everything hanging below it. A dot with no children is a leaf, the end of a branch. A dot that does have children is called an internal vertex. And the subtree at a dot is that dot plus everything below it. Read as its own small tree. We will use all of these words again and again. Let us try the new words on a real family, the Bernoullis. Many of them were famous mathematicians. First question, who is the root? The root is the one dot with nothing above it. That is Nicolaus, born 1623. Second question, who are the siblings of Daniel? Siblings share a parent. Daniel's parent is Johann I. and Johann the First has 3 children. So Daniel's siblings are Nicolaus II and Johann II. Third question. Who are the ancestors of Johann III? We walk up from him to the root. First Johann II, then Johann I, then Nicolaus. Those 3 are his ancestors. 1 tree and 8 questions about it. The tree is rooted at A. Before we answer anything, read the picture. Count the dots. There are 13 from A to M. Count the edges. There are 12, which is 1 less than 13. The Ruta sits at the top and has 3 children. We answer the questions on the next 2 slides, one at a time. Try each answer yourself first. Let us work the first 5 questions, one at a time. First, read the tree. It is rooted at A. It has 13 dots and 12 edges. Now the parent of C look 1 step up from C. We land on B, so the parent of C is B. Next, the children of G look 1 step below G. We find H, I, and J. Next, the siblings of H siblings are the other children of the same parent. The parent of H is G, so the siblings are I and J. Next, the ancestors of E. We walk up from E towards the root. First C, then B, then A. Those 3 are the ancestors. Last, the descendants of B, that is everything hanging below B. Below B sits C, and below C sit D and E, so the descendants are C, D, and E. Now the last 3 questions on the same tree. First, the internal vertices. An internal vertex is one that has at least 1 child. Go through the tree and pick them out. They are a B, C, G, H, and J, that is 6 of them. Next, the leaves. A leaf has no children at all. They are D, E, F, I, K, L, and M, that is 7. Now a quick check. Every dot is either a leaf or an internal vertex, never both. 6 plus 7 is 13, and 13 is exactly the number of dots. Our 2 lists are complete. Last, the subtree at G take G and take everything below it, together with the edges between them. That gives G, H, I, J, K, L, and M read on its own. That is a small tree rooted at G. Now we sort rooted trees by how many children each internal dot may have. A tree is m-ary if every internal dot has at most m children. So a 3-ary tree may have dots with 1, 2, or 3 children, but never 4. It is a full m-ary tree if every internal dot has exactly m children, no more and no less. The most common case is m equal to 2, and we call that a binary tree. So how do you test whether a tree is full? Visit every internal dot and count its children. If all the counts are the same number m, the tree is full m-ary. If even 1 dot has a different count, the tree is not full for any m at all. Let us test 2 trees. The method is always the same. Walk to every internal dot and count its children. Step 0. Read both pictures dot by dot. Start with T1. The top dot has 2 children, the dot below it has 2 children, and the next one down has 2 as well. Every count is 2, so T1 is a full binary tree. Now T2. The top dot has 3 children, each internal dot below it also has 3. Every count is 3, so T2 is a full 3-ary tree. 2 more trees, tested the same way. Step 0. Read both pictures and count children at each internal dot. T3 first. The top dot has 5 children. 2 of those children are internal, and each of them has 5 children too. Every count is 5, so T3 is a full 5-ary tree. Now T4. The top dot has 2 children, but its left child has 3 children. 2 and 3 are not the same number. Since the counts differ, T4 is not full for any value of m. One mismatch is all it takes. So far, the order of the children did not matter. Now it will. An ordered rooted tree is a rooted tree in which the children of each dot are lined up in a fixed order. We draw them left to right, and that drawing is part of the information. The most common ordered tree is the binary tree. Each internal dot has at most 2 children. We call them the left child and the right child. The little tree hanging under the left child is the left subtree. The one under the right child is the right subtree. Let us read one binary tree carefully. First, read the picture. The root is A. Look along every dot. None of them has more than 2 children, so this really is a binary tree. Now the children of D, the one drawn on the left is F, so F is the left child. The one drawn on the right is G, so G is the right child. Now do the same for C. Its left child is H, and its right child is I. Last, the 2 subtrees of C, the left subtree, is the whole tree hanging under H. The right subtree is the whole tree hanging under I. Let us draw both. The first picture is the left subtree. Its root is H, and H has 1 child, J. That is the whole thing. The second picture is the right subtree. Its root is I. It has 2 children, K and L has 1 child, M. 4 dots in all. Notice what we did. We lifted each branch out of the big tree and read it as a tree by itself, with its own root. That habit is what makes the traversal rules later so short. Each rule just says how to handle the root, and then hands each subtree back to itself. Before the next theorem, we need one small fact. Every tree with 2 or more dots has a dot with exactly 1 edge. Recall, the degree of a dot is simply how many edges touch it. Step 1. Among all the paths in the tree that never repeat a dot, take a longest one. It exists because the tree is finite. Call its last dot V. Step 2. That dot has at least 1 edge, the one the path arrived on. The tree is connected and has another dot, so V cannot sit alone. Step 3. Now suppose V had a second edge. Going to some dot X, there are only 2 cases. Either X is not on the path, and then we could walk 1 step further so our path was not the longest. Or X is already on the path, and then the path plus that edge forms a circuit, which a tree never has. Step 4. Both cases are impossible. So V has exactly 1 edge, and its degree is 1. Now the first counting rule. A tree with n dots has exactly n-1 edges. The number of edges is always 1 less than the number of dots. We prove it by induction. That means we check the smallest case, and then show each case follows from the one before. Step 1. The basis. Take n equal to 1. A tree with a single dot has no edges and n-1 is 0, so it holds. Step 2. Assume every tree with k dots has k-1 edges. That is our hypothesis. Step 3. Now take a tree T with k plus 1 dot, so at least 2. By the lemma we just proved, it has a dot V of degree 1. Call its single neighbor W. Step 4. Delete V and that single edge. Nothing ever traveled through V because V had only 1 edge, so every other pair of dots is still joined. And removing an edge cannot create a circuit, so what is left is still a tree, and it now has k dots. By our hypothesis, it has k-1 edges. Step 5. T had exactly 1 more edge, the one we removed. So T has k-1 plus 1, which is k edges. That is 1 less than k plus 1 dots, exactly as claimed. Now a counting rule for full m-ary trees. If such a tree has I internal dots, then it has m times I plus 1 dots in total. Let us build that formula line by line. Line 1. We want in the total number of dots. Line 2. Split the dots into 2 groups. The root is the only dot that is nobody's child. Every other dot is somebody's child. So n is 1 plus the number of children. Line 3. Now count the children from the top down. There are I internal dots and the tree is full, so each of them has exactly m children. That gives I times m children in all. Line 4. Reorder it and we have n equals m times I plus 1. That is the theorem. Theorem 4 takes Theorem 3 further. In a full m-ary tree there are 3 counts. N is the number of dots, I is the number of internal dots, and L is the number of leaves. Know any one of them and the other 2 follow. We do need m to be 2 or more here. If m were 1, the tree would be a single chain with 1 leaf at the bottom. The last row would divide by 0, and the leaf count would tell us nothing. Read the table 1 row at a time. The first row starts from n if you know the number of dots. The internal count is n minus 1 over m, and the leaf count is m minus 1 times n, plus 1, all over m. The second row starts from I if you know the internal count. The total is m times I plus 1, and the leaf count is m minus 1 times I plus 1. The third row starts from L if you know the leaf count. The total is m times L minus 1 over m minus 1, and the internal count is L minus 1 over m minus 1. You do not need to memorize these. On the next slide we build 1 row from scratch, and the others follow the same way. Let us prove the first row of that table line by line. Line 1. We start from Theorem 3, n equals m times I plus 1. Line 2. Solve that for I, move the 1 across and divide by m, we get I equals n minus 1, over m, that is the first formula. Line 3. Now a second fact. Every dot is either a leaf or an internal dot and never both, so n equals L plus I. Line 4. Solve that for L, we get L equals n minus I. Line 5. Put in the value of I we just found. So L equals n minus 1 over m. Line 6. Put both terms over the single denominator m, the top becomes m minus 1 times n plus 1. So L equals m minus 1 times n plus 1 all over m, that is the second formula, and the row is done. Let us try the formulas on a real tree so you can see them work. Read the picture first. Every internal dot has exactly 2 children, so this is a full binary tree and m is 2. Count the internal dots, the ones with children. There are 4 of them. Line 1, so m is 2 and I is 4. Line 2. Use the row for I, the total is m times I plus 1. That is 2 times 4 plus 1, which is 9 dots. Line 3. Same row, leaf column. The leaf count is m minus 1 times I plus 1. That is 1 times 4 plus 1, which is 5 leaves. Line 4. Now check by hand. 5 leaves plus 4 internal dots is 9, and 9 is the total we predicted. Count the dots in the picture and you will find 9. The formulas agree with the drawing. 2 more words, and both are about depth. The level of a dot is how far down it sits. More precisely, it is the length of the path from the root to that dot. The root itself is at level 0 because the path from the root to the root has no edges. The children of the root are at level 1, their children at level 2, and so on. The height of the whole tree is the largest level that any dot reaches, so the height tells you how deep the deepest branch goes. A short, wide tree has a small height. A long, thin tree has a large one. Let us find every level in one tree, and then read off its height. First, read the picture. There are 14 dots. The root is and it has 3 children. Notice that J is a leaf. It has no children at all. Level 0 holds just the root, A. Level 1 holds the children of A, those are B, J, and K. Level 2 holds their children. Under B we find C, E, and F. Under K we find L, so level 2 is C, E, F, and L. Level 3 holds the next layer. Under C comes D, under E comes G, and I, under F comes M, and under L comes N, so level 3 is D, G, I, M, and N. Level 4 holds 1 dot. Under G comes H, nothing goes deeper. The largest level we reached is 4, so the height of this tree is 4. A balanced tree is one whose leaves all sit near the bottom. This is the exact rule. Take an m-ary tree of height h. It is balanced if every leaf is at level h or at level h-1 and nowhere higher up. In plain words, the leaves are packed into the last 2 rows. Nothing stops early, and the test is strict. If even one leaf sits higher than those 2 rows, the tree is not balanced. Let us try it on 3 trees. 2 trees and the same method for both. Find the height first, then list the level of every leaf. Step 0. Read both pictures. Start with T1. Its deepest dot is at level 3, so the height is 3. Now the leaves. Some sit at level 3 and some at level 2. Both of those are allowed because H is 3 and H-1 is 2, so T1 is balanced. Now T2. Its deepest dot is at level 4, so the height is 4. The allowed levels are 4 and 3, but T2 also has leaves at level 2, which is too high. So T2 is not balanced. One more tree worked the same way. First write it. The root has 3 children, so this is a 3-ary tree. Now the height. Follow the longest branch down. The deepest dots are P and Q, and they sit at level 3, so the height is 3. Now the leaf levels. Every leaf of this tree is either at level 3 or at level 2. Nothing sits higher. Level 3 is H and level 2 is H-1. Both are allowed, so T3 is balanced. Theorem 5 puts a ceiling on how many leaves a tree can have. In an m-ary tree of height h, there are at most m to the power h leaves. We prove it by induction on the height. Step 1. The basis. A tree of height 0 is a single dot. It has 1 leaf and m to the power 0 is 1, so it holds. Step 2. Now the hypothesis, and we take the strong form. Assume every tree of height at most h-1 has at most m to the power h-1 leaves. We need the words at most here, because the pieces we are about to make can be shorter than h-1. Step 3. Now take a tree of height h, cut the edges that leave the root. The tree falls apart into subtrees, at most m of them, and each one has height at most h-1. Step 4. Every leaf of the whole tree is a leaf of one of those subtrees. Each subtree has at most m to the power h-1 leaves, and there are at most m subtrees. Multiply, and we get m to the power h. Theorem 5 turns around into a useful lower bound on the height. We take m to be 2 or more, so that the logarithm base m makes sense. Line 1. Start from what we proved. The number of leaves L is at most m to the power h. Line 2. Take the logarithm base m of both sides. Recall the logarithm base m of a number asks, to what power do we raise m to reach it? Logarithms keep the order, so log base m of L is at most h. Line 3. The height h is a whole number, so it must be at least the next whole number up from that logarithm. We write that with the ceiling brackets, so h is at least the ceiling of log base m of L. Line 4, try it. A binary tree, so m is 2 with 8 leaves. Log base 2 of 8 is 3 because 2 times 2 times 2 is 8, so the height is at least 3, and if the tree is full and balanced, the height is exactly 3. Let us see why that second half is true. Now the second half of the corollary, line 1. Suppose the tree is full and balanced, and its height is h, that is all we assume. Line 2. Being balanced means no leaf sits higher than level h-1, so every dot above that level is internal, and being full, every one of them has exactly m children. Row by row, the tree is therefore complete down to level h-1, and that level holds m to the power h-1 dots. Line 3. Look at those dots one at a time. Each one is either a leaf itself, which gives one leaf, or it is internal, and then its m children sit at level h and are all leaves. At least one of them must be internal. Otherwise, the tree would stop at level h-1, and the height would not be h. Line 4. Add them up. The count is more than m to the power h-1, because that one internal dot gives m leaves instead of 1, and it is at most m to the power h by Theorem 5. Line 5. Take the logarithm base m of all three parts, so log base m of L sits above h-1 and at or below h. Line 6. There is exactly one whole number in that range, and it is h, so the ceiling of log base m of L is h, which is what we wanted. Section 11.3. Tree Traversal. To traverse a tree means to visit every one of its dots in a set order. We learn 3 of those orders and then use them to read maths expressions. This is the plan for this section. First, a way to give every dot an address, which we mention only briefly. Then the main topic, the traversal algorithms. Those are the 3 orders for visiting dots. And last, 3 ways to write an expression, infix, prefix, and postfix. They come straight from those 3 orders. Let us set the stage. A traversal is a careful, step-by-step visit to every dot of a tree, each dot exactly once in a fixed order. The 3 most common traversals are Preorder, Inorder, and Postorder. The names tell you when the root gets visited. In Preorder, we visit the root first before any subtree. In Inorder, the root comes in the middle, after the leftmost subtree. In Postorder, the root comes last after every subtree. That single difference is the whole story. We look at each one with a definition, a procedure, and a full run on the same tree. This is the tree we will walk 3 times, once for each order. Read it carefully now, so the runs are easy to follow. Count the dots. There are 16, labeled through P the root is in. The root has 3 children, B, C, and D, so has 3 subtrees, one hanging under each child. Look at C, it has no children, so C is a leaf. Its whole subtree is just C itself. And remember, this is an ordered tree. The children are drawn left to right, and that order is part of the tree. Every traversal rule follows it. Now preorder in full. Let T be an ordered rooted tree with root R. The first part is the stopping case. If the tree is just the single dot R, then the traversal is simply R. Nothing more to do. Otherwise, list the subtrees of R from left to right and call them T1, T2, up to Tn. The rule says, visit the root R first, then traverse T1 in preorder, then T2 in preorder, and so on to Tn. So the short version is easy to remember. Root first, then walk the subtrees left to right. Notice the rule is recursive. Each subtree is handled by the very same rule. This is the procedure for preorder. Read it top to bottom. First we take R, the root of the tree we were handed. Then we list R. To list a dot means to visit it and write it down in the output. Then, for each child C of the root from left to right, we take the subtree rooted at that child and call preorder on it. The procedure calls itself. Now look at where the line list R sits. It comes before the loop. That one placement is the whole difference between preorder and the other two orders. Move that line and you get a different traversal. Let us run preorder on our tree, one step at a time. Step 0. Read the tree first. The root is A and it has 3 subtrees hanging under B, under C, and under D. Step 1. Preorder visits the root first, so we write down A. Step 2. Now the first subtree, the one at B inside it, the root is B, so we write down B. Step 3. Now B's first child is E, so we visit E, then E's first child is J, and J is a leaf, so we write it down too. The list is a B, E, J. Step 4. Back at E, its next child is K, we write down K. Then its 3 children N, O, and P. The list is now a B, E, J, K, N, O, P. We pick the run up where we left it. Step 5. The subtree at E is finished, so we go back to B. Its other child is F, a leaf. We write down F. Step 6. Now the subtree at B is finished, so we go back to the root. The root's next child is C. It is a leaf, so we just write down C. Step 7. Now the last subtree, the one at D, we write down D, then its first child G. Step 8. G has 2 children, L and M, we write both. Step 9. Back at D, its remaining children are H and I, we write them, and now all 16 dots are on the list. The preorder is of B, E, J, K, N, O, P, F, C, D, G, L, M, H. Now in order. Again let T be an ordered rooted tree with root R. The stopping case is the same. If the tree is just R, the traversal is R. Otherwise, list the subtrees left to right as T1 through T, and only one thing changes, where the root goes. We start by traversing T1 in an order. Then we visit the root R, then we traverse the rest, T2 and onward. So for an order, the root sits in the middle, right after the leftmost subtree. Everything else is still left to right, and the rule is still recursive on each subtree. This is the procedure for an order. The first line handles a leaf. If the root R has no children, we simply list it and stop. Otherwise, we take L, the leftmost child, and run an order on its subtree first. Only then do we list the root R. That line now sits in the middle of the procedure, and that is exactly what makes this an order. After the root, we run an order on each remaining child subtree from left to right. Compare this with the preorder procedure. The steps are the same steps, only the position of the line list R has moved. Now we run an order on the same tree. Step 0. Read the tree first. An order always starts at the far left, so follow the leftmost path. A, then B, then E, then J. Step 1. We go all the way down that path. J is a leaf, so we visit it. J is the first dot on the list. Step 2. We come back up one step to E. Its leftmost subtree is finished, so now we visit E. The list is J, E. Step 3. Next comes E's other subtree, the one at K inside it we again go leftmost first, and that is N we write down N. Step 4. Now the root of that little subtree which is K then its remaining children. O and P the list is J, E, N, K, O, P. We continue the Inorder run. Step 5. The subtree at E is finished, and it was B's leftmost subtree. So now we visit B then B's remaining child F, which is a leaf. Step 6. That finishes the leftmost subtree of the root. So now, and only now, we visit A. Step 7. The root's next subtree is the single dot C, so we write down C. Step 8. Now the subtree at D, its leftmost subtree, is the one at G, and inside it we get L, then G, then M. Step 9. That was D's leftmost subtree, so now we visit D, and then its remaining children H and I, all 16 dots are listed. The Inorder is J, E, N, K, O, P, B, F, a C, L, G, M, D, H, I. Now Postorder, the last of the three. Let T be an ordered rooted tree with root R, the stopping case is the same again. If T is just R, then R is the traversal. Otherwise, list the subtrees left to right as T1 through T, and this time we save the root for the very end. We traverse T1 in Postorder, then T2, and so on through Tn only when every subtree is finished do we visit the root R. So the short version for Postorder is, children first, root last. As always, the rule works on each subtree by calling itself. This is the procedure for Postorder, and it is the shortest of the three. First we take R, the root. Then, for each child of R from left to right, we run Postorder on that child's subtree, and only after the loop is finished do we list R. Picture the three procedures side by side. They contain the same lines. Preorder puts list R before the loop. Inorder puts it in the middle. Postorder puts it after. One line, three different traversals. Now the Postorder, run on the same tree. Step 0. Read the tree with the Postorder rule in mind. Every root has to wait until all of its children are done. Step 1. So we go deep to the left down to the leaf J and visit it. J is first on the list. Step 2. Next comes K's subtree. Its children N, O, and P are leaves, so they go first. Step 3. Now K's children are all done, so we may visit K itself. Step 4. That finishes both of E's children, J and K, so now we visit E, then we move to B's other child. The leaf F, the list is J, N, O, P, K, E, F. We finish the Postorder run. Before we do, pause the video for a moment and guess which dot will be listed last. Step 5. Both of B's children are now done, so we visit B. Step 6. The root's next subtree is the single dot C, so we write down C. Step 7. Now the subtree at D inside it, G's children L and M come first, and then G. Step 8. Then D's other children, H and I, now all of D's children are done, so we visit D. Step 9. Every subtree of the root is finished, so at last we visit A. Did you guess? The root comes very last, and that is the signature of Postorder. The full order is J, N, O, P, K, E, F, B, C, L, M, G, H, I, D, A. Trees give us a clean way to store a maths expression. We use an ordered rooted tree, and we call it an expression tree. Take this expression. In brackets x plus y, close bracket, raised to the power 2, plus, in brackets x minus 4, close bracket, divided by 3. The rule for building the tree is simple. The numbers and letters, called operands, become the leaves. The operators like plus, minus, and divide become the internal dots. Each operator sits above the two pieces it combines. Look at the picture, and you can see the whole expression laid out. One small point. Rosen's textbook writes the power operator as an up arrow. These slides use the caret sign instead. They mean the same thing. Let us read the expression tree, one part at a time. First, read the whole picture. There are 11 dots. 5 of them are operators and 6 are operands. Now the root. The root is a plus sign. The root is always the last operation you would carry out because it combines the two finished halves. Now the left subtree. Its top is the power operator. Below it sit the bracket x plus y and the number 2. So the left half is x plus y, all raised to the power 2. Now the right subtree. Its top is the divide sign. Below it sit the bracket x minus 4 and the number 3. So the right half is x minus 4 divided by 3. And to evaluate the tree, you work bottom up. Start at the leaves, combine each pair, and climb until you reach the root. Reading an expression tree in Inorder gives the infix form. Infix is the normal way we write maths, with the operator sitting between its two operands, like x plus y. But infix on its own is not enough. To make it unambiguous, we must add parentheses. Unary operators are the one exception. They simply follow their operand. Why do we need those parentheses? Because different trees can read out as the very same string once the brackets are dropped. On the next slide, we build 3 trees that all do exactly that, and yet compute 3 different values. These are 3 trees. They have different shapes, so they mean different things. Let us read each one twice, once with brackets and once without. The first tree. Its root is a divide, so it means in brackets x plus y divided by in brackets x plus 3. Now read it in Inorder and drop the brackets. You get x plus y slash x plus 3. The second tree. Its root is a plus and its right side is the number 3. So it means in brackets x plus y over x close bracket plus 3. Read it in Inorder without brackets, and you get x plus y slash x plus 3 again. The third tree. Its root is a plus and its left side is just x, so it means x plus y over in brackets x plus 3. Drop the brackets, and once more you get x plus y slash x plus 3. 3 different meanings, one identical string. That is why infix needs its parentheses. Now prefix notation. Read the expression tree in preorder and you get the prefix form. It is also called Polish notation, after the Polish logician Jan Łukasiewicz. In prefix, the operator comes before its two operands, and no parentheses are needed at all. The order of the symbols carries the whole structure. For our example expression, the prefix form is plus caret plus x y2 slash minus x 4 3. To evaluate a prefix expression, scan from the right. Whenever you meet an operator, apply it to the 2 values sitting just to its right, and replace all 3 symbols by the answer. Let us run it. Let us evaluate one prefix expression, step by step. Step 0. Read it first. 11 symbols. We scan from the right and stop at the first operator that has 2 numbers on its right. Step 1. Moving in from the right, the first such operator is the caret. To its right sit 2 and 3. 2 to the power 3 is 8. We replace those 3 symbols by 8. Step 2. Now the next operator to the left is the slash. To its right sit 8 and 4. 8 divided by 4 is 2. Step 3, next is the star. To its right sit 2 and 3. 2 times 3 is 6. Step 4, next is the minus. To its right sit 6 and 5. 6 minus 5 is 1. Step 5, last is the plus. To its right sit 1 and 2. 1 plus 2 is 3, so the value of the whole expression is 3. Last comes postfix notation. Read the expression tree in Postorder, and you get the postfix form. It is also called reverse Polish notation. Here the operator follows its two operands, and again, no parentheses are needed. For our example, the postfix form is x y plus 2 caret x 4 minus 3 slash plus. To evaluate a postfix expression, scan from the left. Whenever you meet an operator, apply it to the two operands just before it and replace all three symbols by the answer. This is exactly the mirror of the prefix rule. Let us run it. Now the same job for a postfix expression. Step 0. Read it first. 11 symbols again. This time we scan from the left and stop at the first operator that has two numbers just before it. Step 1. The first operator we meet is the star. The two numbers before it are 2 and 3. 2 times 3 is 6. Step 2. Next comes the minus. The two numbers before it are 7 and 6. 7 minus 6 is 1. Step 3. Next comes the caret. Before it sit 1 and 4. 1 to the power 4 is 1. Step 4. Next comes the slash. Before it sit 9 and 3. 9 divided by 3 is 3. Step 5. Last comes the plus. Before it sit 1 and 3. 1 plus 3 is 4, so the value is 4. Section 11.4. Spanning trees. A spanning tree is a tree hidden inside a bigger connected graph, one that still reaches every dot. We define them and then learn two ways to build one. This is the plan for this section. First, what a spanning tree is. Then our first method to find one, depth first search. Then the second method, breadth first search. Then a quick word on backtracking, which we only mention. And last, depth first search on directed graphs, where the result is a forest instead of a single tree. Now the main idea of this section, the spanning tree. Take a simple graph G. A spanning tree of G is a subgraph that is a tree and still touches every dot of G, so it is a skeleton that connects everything, with no loops left over. Read the graph on the screen. It has 7 dots through G and 9 edges. It is connected so you can get anywhere from anywhere. But 9 edges is too many. A tree on 7 dots must have exactly 6 edges, so there are loops in here and we will have to break them. Let us do that carefully on the next slide. Let us build the spanning tree, one edge removal at a time. Step 0. Read the graph. 7 dots and 9 edges. A tree on 7 dots needs exactly 6 edges, so we must remove 3 and each one must be taken from a loop. Step 1. Find a loop. Follow it to B to F, F to E, and E back to A, that is a circuit. Remove the edge between A and E. The two ends are still joined through the rest of the loop, so nothing gets cut off. 8 edges left. Step 2. Find another loop. The dots E, F, and G form a triangle. Remove the edge between E and F, 7 edges left. Step 3. One more loop. The dots C, F, and G form a triangle too. Remove the edge between C and G, 6 edges left. Step 4. Now search for a loop and you will not find one. 6 edges, 7 dots, and everything still connected. That is exactly a spanning tree. This is the result, drawn in green. Trace it and check the two words for yourself. Is it connected? Start at A, you can reach B, then F, and from F you can reach C, G, and on to D and E. Every one of the 7 dots is reachable. So yes, it is connected. Does it have a loop? No, every removal we made broke one, and we added nothing back. And count the edges. There are 6 for 7 dots. That is 1 less than the number of dots, exactly as Theorem 2 promised. So this really is a tree, and it spans the whole graph. Now a clean theorem. A simple graph is connected exactly when it has a spanning tree. It is an if and only if, so we prove it in 2 directions. Step 1. Start with the easy direction. Suppose G has a spanning tree T. By definition, T reaches every dot of G. Step 2. Inside T there is a path between any 2 dots, and T sits inside G, so those same paths live in G, so G is connected. Step 3. Now the other direction. Suppose G is connected. If it is already a tree, we are done. If not, it must contain a circuit. Step 4. Remove one edge of that circuit. Removing an edge from a loop never disconnects anything, because the 2 ends are still joined through the rest of the loop. Step 5. Keep doing that until no circuit is left. What remains is connected, has no loops, and still reaches every dot. That is a spanning tree. Now our first method, depth first search, or DFS for short. The idea is to go as deep as you can, then back up when you get stuck. Step 1. Pick any dot to be the root. Step 2. Build a path by walking forward. Each new edge must lead to a fresh dot, one not already visited. Keep walking as long as there is a new dot to reach. Step 3. If your path has caught every dot, you already have a spanning tree. Step 4. If some dots are still missing, back up 1 step to the previous dot and try to start a new path from there. If you cannot, back up 1 more step. Step 5. Repeat until every dot is in the tree. In short, go deep, and when you cannot go further, back up and try another branch. This is the graph we will search. Read it before we start. Count the dots. There are 11 labeled through K. Count the edges. There are 12. A tree on 11 dots needs exactly 10 edges, so the search will choose 10 of these 12 and leave 2 out. We are free to start anywhere. For this run we start at F, near the middle. Watch how the search walks away from F as far as it can go, and then comes back. Let us run the search, step by step. Step 0. Read the graph, 11 dots. We choose F as the root, so F goes into the tree first. Step 1. Now walk as deep as we can. From F we reach G, from G we reach H, from H we reach K, from K we reach J. 5 dots are in. Step 2. At J there is nothing new to reach, so we back up. At K still nothing new. Back up again to H, from H we can reach I, which is new. Added, 6 dots. Step 3. From I nothing new. Back up to H, then to G, then to F. From F we can still reach D, which is new. Add D, then E, then C, then A. 10 dots. Step 4. Add a nothing new. Back up to C. From C we can reach B. Add it, 11 dots. Step 5. Every dot is now in the tree, so we stop. Count the edges, 10 of them for 11 dots, exactly right. This is the tree the search built, redrawn with the root F at the top. It holds exactly the edges we chose during the run and nothing else. 10 edges, 11 dots. Look at its shape. It is deep and thin, with long branches running down. That comes straight from the rule we followed. We always walked on while we could, and only backed up when we were stuck, so the tree stretches downward rather than spreading sideways. The graph has to allow it, of course. If every dot were joined to the root and to nothing else, even depth-first search would give one wide, flat tree. Remember this picture. When we run breadth-first search on another graph, the tree will look very different. When depth-first search finishes, it splits the graph's edges into two kinds. The edges it actually chose are called tree edges. We draw them as heavy blue lines. There are 10 of them. Every other edge of the graph is left over. Each leftover edge joins a dot to one of its own ancestors or descendants in the tree. Those are called back edges, and we draw them thin and gray. In this figure, the two back edges are the edge EF and the edge FH. The graph had 12 edges and the tree uses 10. 12 minus 10 is 2, so exactly 2 are left over. And one handy fact, a back edge always runs up or down the same branch, never across to a different branch. Depth-first search guarantees that. This is the procedure for depth-first search. We start with a tree T that holds only the first dot, V1. Then we call visit on V1. The visit procedure does the real work. For each dot W that is next to V and not yet in the tree, we add W and the edge from V to W, and then, straight away, we call visit on W. That last part is the key. After we step from V to W, we fully explore W and everything below it before we ever come back to V. That is what going deep first means, and it is why the procedure calls itself. Recall recursion just means a procedure that calls itself on a smaller piece of the same problem. Now the second method, breadth-first search, or BFS. This time we grow the tree in layers, staying wide instead of going deep. Step 1, pick any dot to be the root. Step 2, add every edge from the root and the dots at their other ends. Those new dots make up level 1. Step 3. Take the dots we just added, one by one, and add each of their edges that does not close a loop. The fresh dots we reach make up the next level. Step 4. Keep going, one full level at a time until every dot is in the tree. So the difference from depth-first search is simple. Depth first goes as deep as it can. Breadth first fills one whole level before starting the next. This is the graph for our breadth first search. Read it first. Count the dots. There are 13, labeled A through M. Count the edges. There are 17. A tree on 13 dots needs exactly 12 edges, so the search will keep 12 of these 17. We root the search at E, which sits near the middle and has 4 neighbors. Watch how the tree grows outward from E in rings, one whole ring at a time. Let us run breadth-first search, one level at a time. Step 0, read the graph 13 dots. We root the search at E, so level 0 is just E. Step 1, add every neighbor of E. Those are B, D, F, and I together. They make level 1. Step 2, now we work through the level 1 dots in order. From B we reach on C, both new. From D we reach on H, but it is already in, so we only add H. Step 3. From F we reach G and J, both new. From I we reach H, J, and K, but H and J are already in, so we only add K that completes level 2, a C, H, G, J, and K. Step 4. One more ring. From G we reach L, from K we reach M, those two make level 3. Step 5. All 13 dots are now in the tree, so we stop. Count the edges, 12 for 13 dots, exactly right. This is the tree that breadth-first search built, drawn with the root E at the top. Each row of the picture is one level of the search. Level 1 holds B, D, F, and I level 2 holds a C, H, G, J, and K level 3 holds L and N. Now compare this shape with the depth first tree from earlier. That one was deep and thin. This one is wide and shallow. Counting the root, it has 4 rows from level 0 down to level 3, so its height is 3. That difference is not an accident. Breadth first search always finishes a whole ring before moving outward, so every dot ends up as close to the root as the graph allows. This is the procedure for breadth first search. We start with a tree T holding only the first dot, V1. We also keep a list L of dots waiting to be processed, and we put V1 in it. Then, while the list is not empty, we take the first dot off the front and call it V. For each neighbor W of V, we check whether W is already in the list or already in the tree. If it is in neither, then W is new. We add it to the back of the list, and we add W and the edge from V to W to the tree. Look at the two ends of the list. We always take dots from the front, and we always add new ones to the back. That is what keeps the search moving level by level. Last, we run depth first search on a directed graph. Both searches still work when the edges have arrows, but there is a catch. You may not be able to reach every dot from one starting point, so the result may be several trees side by side, which we call a spanning forest. This idea powers web spiders. A search engine explores the web by starting at known pages and following links, and a link is a directed edge. If the start does happen to reach every dot, you still get a single tree. Read the graph now. 12 dots, a through L, and every edge carries an arrow. From here on you may only travel in the direction of the arrow. That single restriction is what can break the result into pieces, and in this graph it does. Let us build the forest, step by step. Step 0. Read the graph. 12 dots, and every edge is an arrow we must follow forwards. Step 1. Start at A, follow arrows as deep as we can. From A to B, from B to C, from C to G, then back up and take B's other arrow to F, and from F to E that gives our first tree with 6 dots. A, B, C, G, F, and E. Step 2. 6 dots are still unvisited. None of them can be reached from A, so we simply start again at the first one left, which is D from D to H, from H to L, from L to K, from K to J, that is our second tree, with 5 dots. Step 3. Only I is left. Its arrows point to E and to J, and both of those are already visited. So I cannot join anything. It becomes a tree all by itself. Step 4. Count up. 6 plus 5 plus 1 is 12, so every dot is placed. 3 trees together make a spanning forest. This is the finished forest, drawn in green. The first tree is rooted at A, it holds 6 dots, and its arrows show the order we walk them. The second tree is rooted at D, it holds 5 dots in one long chain. The third tree is rooted at I, and it holds only I. Together they cover all 12 dots, and they use 9 edges in total. Notice that is not 12 minus 1. A forest with 3 trees has 12 minus 3 edges, because each tree loses 1. So remember the rule. On an undirected connected graph, the search gives one spanning tree. On a directed graph, it gives a spanning forest, because one starting dot may not reach everything.